Good day, everybody. I am Surojit Das, a PhD student from Infochemistry Scientific Center at ITMO University, St. Petersburg. First of all, I would like to thank the organizing committee of DESE IEEE 2025 for providing me with the opportunity to give this talk, and I would like to convey my regards to the session chair and all other attendees. Today, I am going to present an intelligent software system for low-cost bright field image segmentation. The scope of this talk is primarily focused on the algorithmic implementation for cytometric auto-analysis rather than on a theoretical algorithmic discussion. The motivation of our work is grounded in the fact that while bright field microscopy is essential for low-budget labs, it produces noisy, low-contrast images of unstained live cells. This poses a significant challenge to the analysis which involves segmentation, feature extraction, etc. Furthermore, these labs often lack both GPU resources and skilled programmers. This creates a clear need for a practical CPU-based and user-friendly tool for label-free analysis. This is exactly what we have developed. Our key contributions include a CPU-based microscopy image analysis framework on label-free data. We provide a cross-platform interface, a easy-to-use GUI for non-programmers, and scripting support for advanced users. Key features include end-to-end segmentation, feature extraction, and automatic reporting. Existing state-of-the-art models have several limitations. Moreover, all these tools fail to handle the noisy, low-contrast, bright-field microscopy images of live cells, and none of the tools generates the automated report. Therefore, evidently, the persisting gaps remain with poor generalization due to inappropriate uncertainty quantification, a lack of explainability, strong dependency on GPUs, and complex interfaces or script-based access which make them difficult for non-programmers to use. The existing SOTA models are well equipped for quantifying aleatoric uncertainty. However, they do not adequately model the constraints associated with epistemic uncertainty. This is because most fundamental neural network algorithms rely on either hard assignments or classical probabilistic measure, for example, Bayesian rule, which constitutes a considerable limitation measuring epistemic uncertainty. The most current SOTA models lack explainability due to their reliance on artificial neural networks. The inherent black box nature of ANNs, characterized by opaque decision-making processes, poses a significant challenge to explainable AI. The complex high-dimensional transformation within ANN is inherently difficult to interpret, requiring the use of post-hoc explanation techniques. However, the integration of these techniques often remains an afterthought in the development of SOTA models. Other problems remain with GPU and script constraints. Most current tools heavily depend on GPUs and large labeled datasets, which limits their use in low resource labs. On top of that, their complex or missing GUIs make them difficult to operate in non-coding environments, leveraging many biologists unable to fully leverage these powerful methods. The software system consists of four modules: segmentation module, post-segmentation denoising module, instant analysis, and automated reporting. Each module can be executed individually through the GUI or a scripting interface. However, they can work sequentially in automated environment. The system is based on the DAS-Zoon HIP model, which addresses uncertainty more effectively through fuzzy logic and various spatial statistical metrics. In their paper, DAS-Zoon has demonstrated that the model significantly outperforms SOTA models on complex and ambiguous datasets. The system's performance has been validated on several datasets. The results demonstrate that the model produces competitive results and often outperforms SOTA models. We have included the scores obtained from testing on a public live-cell dataset. In the next few minutes, we will experience a live demonstration of the software system.
Welcome to the live demonstration of microscopy image analysis. First, we show the output folder, which is currently empty. The input folder contains a subfolder named 000, and inside it, there are 3 images to be segmented. These will be processed through automated batch analysis using the Interface Profile Manager. Before we begin the batch process, we click Open Image under the Action tab to open an image for semantic segmentation. Then we click Semantic Segmentation under the Action tab. Immediately a progress bar approaches down the wide gate and starts the semantic segmentation. A console appears displaying the status. The steps and different stages of semantic segmentation are displayed during this process. Here the system yields the first intermediate output based on the probable homogeneous image plane, which is a very rough roadmap to the system. Once semantic segmentation is finished, we navigate inside the output folder and find a new subfolder named Result, which contains the output of semantic segmentation. This image is noisy, so we use the next module named Post-segmentation for denoising to remove the noise. So, we click Post-segmentation processing under Action tab. The system opens the output of semantic segmentation output. Then start the post-segmentation denoising, applying erode, fill below threshold, circularity, and median filter. Finally, we save the processed image by clicking Save Image. We can click the Operation History to see the operations performed and can save them as a profile for future use by clicking the Save Profile button. This is a one-time step. For example, we have used only 2 different profiles for end-to-end segmentation of 3,180 images of public live cell dataset. Then we click Exit and revisit the Result subfolder under the Output folder to verify the processed image, which is now clean. Next, we perform instance segmentation by clicking Instance Segmentation under Action tab and immediately find the output. An annotated image is on the left side while the output with the bounding box is found on the right side. We also verify the Result subfolder to ensure the outputs of instance segmentation have been saved. Finally, by clicking Report under the Action tab, we generate a report inside the Result folder. This system turns raw data of extracted features into an interactive report which includes descriptive stats, quartiles, univariate distributions like histograms, box plots, and multivariate scatter plots, heat map, etc. Results from an interactive HTML dashboard with toggles for focused review, ensuring rigor in PDF export. As open source, it offers researchers reproducible workflows that speed exploratory data analysis. For multiple images, we automate the process by clicking the Profile Manager under the Action tab, then select the input directory, 000, in this case. Finally, we select the profile which we have saved already and hit the Run Batch Process button. A dialog box with progress bar indicates the overall progress of end-to-end segmentation and analysis of 3 images. Two images out of 3 are completed and the last image is under process. Yes, it is complete now. In the output folder, 3 distinct folders have been created. Let's check anyone. Yes, all the stuff is there. We find the report, results of instance segmentation, extracted features, etc. Although by default the system extracts a few features. The complete list is quite long and users can customize it. So, this is how this intelligent software system works. Thank you for watching the demonstration. Have a nice day.